So, good morning to all of you.
Good morning, sir.
Good morning, sir.
Good morning.
Morning, sir.
So, how have you enjoyed your induction program? Is it all right? Hello? Can you hear me?
Yes, sir.
Yes. Yes,
So,
sir.
how you have
Yes, sir.
enjoyed your induction program?
Yes, sir. We enjoy.
Yes.
Yes, sir. We enjoy.
Okay. So, I think yesterday we had a meeting with director. So, I think we expected that you will come to the campus in the next semester, that is for this semester, current semester. But unfortunately, as you know, due to Omicron and COVID-19, so we have to postpone that proposal. And I hope in the after mid semester, we will again consider the situation, and we are very much interested to see you in the campus with physical mode class teaching. Okay, so right now we have to continue only this online teaching, and the last class I missed somehow because I was also busy in that your induction program, in organizing the program. So anyway, so I'll take any suitable extra class if you like. You can give if you decide suitable date, and I can continue, no problem. Okay. So actually, I will take your physical chemistry course. That is chemical kinetics and electrochemistry. And many of you are familiar with these topics, right? So I'll start first chemical kinetics, basic background. Okay. So I'll present something. Yes. Actually, I have not taken the pen, so so you can start today, starting from here. So basic things we'll discuss, and I think many of you are familiar with these topics. Okay. So you know in general that rate of a chemical reaction is generally expressed like that in general, but it is not always correct because most of the reactions that we know that are multi-step reactions and they are complicated in nature. That means these reactions take place through several intermediate or consecutive steps. And so rate law is somewhat complicated, and in those cases, from the inspection of the rate law, it is very difficult to say what is the order of the reaction, right? But here at the very beginning that we use the general rate equation. This are rate equal to k into a to the power alpha, b to the power exponent c, beta, c to the c raised to the power gamma. So this is the general reactions that we have considered. The reactant A, B, and C, they react to produce products D and E. Now you know that what is the overall order of the reaction? That is the sum of the exponents that appear in the rate equation that we call overall order of the reaction. But alpha, beta, and gamma, say alpha will say it is the reaction is alpha order with respect to reactant A, it is beta order with respect to reactant B, and it is gamma order with respect to reactant C. Now, how to find out these coefficients, the exponents, that is alpha, beta, and gamma? So, in general, these quantities are determined from experimental measurement of the kinetics of that particular reaction. So basically it is an experimentally determined quantity. And sometimes it can also be guessed in rare cases based on some theoretical models, and we can explicitly explain and the rate law, and from there we can also guess what should be the overall order of the reaction. Now here K we call, as you know, it is called rate constant, right? K is called rate constant. And you know rate constant depends only on temperature. It does not depend on reaction temperature. Yes?
Sir, will you not record the class?
Actually, in the tab I am taking the class. In my tab, I cannot record. That is the problem. So
Okay.
you can give your attendance to chat, right?
Okay, sir.
You can give your attendance to chat. That is the problem, because I have the laptop, but that Wi-Fi has some problem. So sound system is not properly working. That is the problem. Otherwise, video is okay.
Okay, sir.
Otherwise, so I am taking your class in a small tab, but I can write everything here. I can erase something here. But today I need to take my pen, and I am now staying far apart from my home. So that is the problem. Anyway, so I think from the next class it will not be any problem. And if you have any query or any question, you please raise your question. Right. Now the exponent, I think something disturbance is coming. Please mute your unmute. Mute if you have any problem. Okay. So this, what is the unit of K, rate constant of nth order reaction in general? So it is given as a general expressions, as you know, that is K rate constant. It has the unit liter raised to the power n minus 1. mole raised to the power 1 minus n and second inverse. Right. It may be minute inverse, it may be hour inverse, any time, depending on the scale you are using. Okay. Say if I ask you what is the rate constant of a zeroth order reaction? What is the unit?
Sir, mole per liter per second.
Yes. For first order reaction?
Inverse.
Second
Inverse.
Second inverse.
Independent of
concentration.
Okay.
Second inverse.
Okay. Now, in general, we can write a chemical reaction, a balanced chemical reaction in a compact form, just like algebraic equation, right? That is written summation I nu I AI equal to 0. What is the AI? AI stands for formula of a reactant or product species. AI subscript I represents the formula of a reactant or product species. And what is nu I? Nu I is the stoichiometric coefficient in the balance reaction. Nu I is the stoichiometric coefficient associated with reactant A I in the balanced chemical equation. I can give you one example of an occurrence. Now, what is nu I? Nu I may be greater than 0, and this is for product. And nu I may be less than 0, then we say it is associated with reactant. Okay, so nu I AI, sum of nu I AI equal to 0. Here, nu I we call stoichiometric coefficient in the balance reaction or chemical equation. And so the sign of nu I depends on the whether it is product or reactant. I can give you one explicit expression. Okay. Then it will be clear to you. Say for example, formation of ammonia from nitrogen and hydrogen. So this is a balanced chemical equation. And we can rearrange this equation. We can rewrite it in the form just like algebraic fashion. That is 2 NH3 minus N2 minus psi H2 equal to 0. Right? Now, in this equation, I think you can understand that NH3 is the product and its coefficient 2, stoichiometric coefficient 2 is positive. Right? Likewise, nitrogen and hydrogen, they are reactants. And the stoichiometric coefficients that appear here are negative. So that's why I have mentioned it that nu I, that stoichiometric coefficient is greater than 0 when it is associated with a product. And nu I, that stoichiometric coefficient is negative when it is associated with a reactant species. Is it clear? Or if you have any doubt, you can raise any question, please. Okay. Now, the purpose of writing this equation in this compact form is going to be clear to you. So, we just write this equation. Now, let Ni, what is Ni? Once again, we consider this equation, that is nu I AI equal to 0. Summation I nu I AI equal to 0. Or in general chemical reaction, it is a representative one. Okay. Now, Ni, what is Ni? Small Ni represents the number of mole numbers of I reactant species. Number of mole numbers at any instant during the progress of the reaction, at any time. And what is Ni superscript 0? Ni 0 indicates the number of moles of that reactant species at the start of the reaction. Okay? Plus nu I into epsilon. What is epsilon? Epsilon is a quantity we call degree of advancement of a reaction. Degree of advancement means it is a parameter which measures quantitatively the progress of the reaction. That is how much the reaction already progressed or completed. That can be traced by following this quantity or parameter. That is called the degree of advancement of a reaction. It is denoted by epsilon. Right. So, Ni equal to nu I 0 plus nu I stoichiometric coefficient into epsilon. Now, again it is clear that for reactant species it would be a negative quantity, that is Ni 0 minus nu I epsilon, and if it is a product then naturally mole numbers will increase compared to initial mole numbers, then naturally nu I should be positive. Right. So at this stage, if you have any doubt, please ask any question. Do you have any confusion at this stage?
Sir, please tell about Ni and Ni not.
Ni is the number of mole numbers of reactant species, say here denoted by Ai. Say a particular reactant Ai. What is the initial mole numbers of that reactant? That is before the start of the reaction. That is denoted by Ni superscript 0. But Ni, what is Ni? Ni is the number of moles of that particular species, that is Ai, after the start of the reaction. And any time you can measure. So that means Ni is a variable quantity. As the reaction progresses, there is degree of advancement increases, epsilon, Ni may increase for reactant, for product species. With increase in epsilon, Ni will decrease for reactant species. Right? Compared to its initial mole numbers.
Okay, sir.
So that's why Ni equal to Ni 0 plus nu I epsilon. Nu I is the stoichiometric coefficient in the chemical reaction of that particular species Ai. So it is a constant quantity. Ni is 0, it is the starting mole numbers of reactant or product. It is also a constant quantity. It will not change as the reaction progresses. Okay, and only the quantity Ni, that is the number of moles of that species, that is the I species, as the reaction progresses. Okay, alright. So that's why when differentiating this, we can write dNi equal to, because Ni0 is constant, so it will be 0. So dy into d epsilon. Okay, so we can write it in this form, that is dNi. If we differentiate with respect to time, that is dNi dt equal to dy into d epsilon dt. Right? Now, this can be rearranged in this form, d epsilon dt equal to 1 by dy into dNi dt. Now we divide both sides by volume of the container where the reaction is carried out. Right. What is V? V is the volume where the particular reaction has been carried out. So we divide both sides of this equation by a constant value V, volume V of the container. And in the right hand side, you see What is that? 1 by nu I dCi dt. What is Ci? Ci is the concentration.
Concentration.
Molar concentration, right? Number of moles per unit liter, per unit. So Ci equal to Ni by V. So, and the left hand side, that quantity d dt of epsilon by V, this is called unique rate. Unique rate. Unique rate represents what? So that means for a particular reaction, if you note that there are several reactants and several products, right? If it is a single step reaction, suppose, for simplicity, I say this is a elementary reaction. Elementary means a single step reaction. And suppose if there are more than one reactant or more than one product with different stoichiometric coefficients, then what we can say that the rate, if you follow with respect to a particular reactant or a product, it would be not identical. Say for example, say formation of ammonia. If I say what is the rate of reaction with respect to nitrogen? Look, if we say that in 1 second, 1 molecule of nitrogen reacts or consumes. At the same time, at the cost of 1 molecule of nitrogen, 3 number of H2 molecules is consumed. And subsequently, 2 number of ammonia molecules is replaced. So if we follow the rate, that is number of molecules changes per unit time, that is second. So naturally the rate with respect to N2 will be less, 3 times less compared to hydrogen, right? And also 1 by half times of the rate of formation of ammonia, right? So that means if you specify the reaction rate with respect to a particular reactant, then we see as if the reaction rates are different. So that's why we had to decide or propose the unique rate of the reaction. And how we can define the unique rate? Unique rate we can define irrespective of the reactant, whether it is any reactant or in terms of any product, but we can define that in an expression that we call unique rate. Say for example, that I'm giving here, what I'm discussing right now. So rate of reaction, which is unique. Look, whether we express it in terms of nitrogen or hydrogen or ammonia, you see in all cases, this unique rate as we defined just now can be written like this. That is rate of the overall reaction, the unique rate of the reaction is equal to 1 upon minus 1 d into concentration N2 dt equal to minus 1/3 d of H2 by dt equal to half d NH3 dt, where t is the time. So this is the unique rate law, how to represent it, that we have discussed. Okay, I think it is clear to you, and you are familiar with this discussions earlier in your last class. Sorry. Anyway, so first order reaction. Now I will give you examples of first order reactions, second order reactions, like that. And these are familiar. You know, decomposition of nitrogen pentoxide. It follows a first order reaction, but it is not so simple first order, straightforward first order reaction. Straightforward means it is not a single step reaction, right? Although it seems that these are simple reactions, but these reactions are not simple at all. They take place more than one step, and those mechanisms I will discuss later on. Okay. Likewise, decomposition of ethyl bromide to ethylene and hydrogen bromide. This is also a first order reaction. This reaction follows first order kinetics. Now second order reactions, typical examples that I can give you, say formation of hydrogen iodide in the gas phase from hydrogen and iodine, right? So these reactions should be carried out in the gaseous state. So formation of HI from its constituent elements. Likewise, decomposition of HI to H2 and I2 both follows second order kinetics, whether it is formation of HI or decomposition of HI. Likewise, formation of ethane from ethylene and hydrogen follows a second order kinetics. Another popular second order kinetics you may be familiar with, that is ethyl acetate is hydrolysis in alkaline medium. Right. Decomposition or the hydrolysis of ethyl acetate in alkaline medium. It gives acetate ion and ethanol. Right.
Sir, order of reaction is determined experimentally or theoretically?
Yes. Order of all these reactions can be determined experimentally. Right. And
Okay.
I think the esterification, the hydrolysis of ester, it is a popular reaction that could be studied in the laboratory. So you can find out that after studying the experiment that it follows the second order kinetics, that is hydrolysis of ester. Okay.
Sir, hydrolysis ester sometimes was known as pseudo first order.
Yes, that you are right. What is pseudo first order? That means if you take one of the components in large excess, that will be acid constant. That I can give you example. Pseudo first order means basically this is a second order reaction. But if one component is taken large excess, then that concentration will remain invariant and it will be first order with respect to other component which is present in small extent in the reaction mixture. Okay. So those reactions are pseudo unimolecular. That is different. Okay. Particularly hydrolysis of esters in acid medium, that I can give you example. That's typical example. Now this is a third order reaction. In the third order reactions, we see formation of nitrosyl chloride from nitric oxide and chlorine. Likewise, formation of nitrous oxide into O from NO and H2. And the formation of NO2, brown gas NO2 from NO and O2. So these are the typical third order reactions. And once again, I'm repeating that these reactions do not take place in a single step. That is very important. None of these reactions could take place in a single step. That is very important, right? But overall, they follow third order. Now, zeroth order reaction. What is zeroth order reaction? That is the reverse of the Haber reaction. This follows zeroth order kinetics. And zeroth order kinetics in general, how to represent and what is the kind of that kinetics that you can easily trace. Suppose, as usual, for reactant to product R to P, here R represents a particular reactant, P is a particular product. Okay, and this rate of this reaction is, as you are familiar with, in that form I am writing minus D concentration R dt equal to K reactant concentration raised to the power 0 because it is zeroth order kinetics. So that means basically minus dr dt equal to K. So that means physically what does it mean? That is traced in the graph. If we plot reactant concentration versus time, then the slope is naturally negative, is a constant, just like a straight line, right? And it would be, look, now the question is, this reactant concentration will gradually falls to 1. If you increase the time, the reactant concentration R0, that is initial reactant concentration, will gradually decrease. And ultimately, it would tend to 0. Right. But, so this trend you can expect only reactant to product if we consider the reaction not reversible, that is unidirectional. Then only it would follow this kinetic perfectly like this. That means reactant concentration would tend to 0 when time increases, right, at the limiting value. So for larger value of T, you can expect the concentration of our reactant goes to 0. But most of the reactions, as you know, they are not unidirectional. They are reversible, and that's why this plot is not always correct. But it is true if we consider for the kinetic study. That is, we are focusing or we are considering only the forward reactions, ignoring the backward reactions in the kinetics. Right. So this is the plot, the first zeroth order kinetics. Now, first order kinetics, you are familiar with reactant to product. And as you know that it can be written like this, differential rate equation, that is minus dr dt equal to a reactant concentration R. And if you integrate it, you will get it in this exponential form, that is reactant concentration. In the left hand side, R denotes concentration of reactant at any time, and R0 is the initial concentration of that particular reactant, e to the power minus kT. K is the rate constant and T is the time. So it is straightforward to integrate, and you will get it like this, that integrated rate equation. Right. And now we introduce a quantity that we call T5. What is T5? T5 is the fractional lifetime. Fractional lifetime means what? Say phi is the fraction by which the product decreases by 5 times. Right. So can we write this equation in this form? That is T equal to 2.303 by K log 10 base, exponential to log 10 base, natural logarithm to 10 base. Instead of E, if we take 10 as a base of log, then it would be written like this, time T equal to 2.303 by K log concentration of reactant at any time to the reactant at 0 time. Sorry. In the numerator, it is R0. That is, suppose you forget sometimes whether it will be R0 by R or R by R0. That you can easily guess, because as the reaction progresses, the reactant concentration simply represented by R, its concentration will be much less than R0. So this ratio would be naturally fraction if we take in the reverse way, that is R by R0, and log of any fractional quantity is a negative quantity. So time cannot be negative, right? So from that you can show that it should be R0 by R. Suppose if you forget the formula, that's something. Otherwise it is straightforward that you can rewrite that equation. Okay. So for fractional lifetime T5, phi may be half, say 2/3, 1/3 like that, it can be represented like T phi equal to 1 upon k into log 1 upon 1 minus phi. The interesting point is that in the equation, you see that the fractional lifetime, it does not depend on the initial concentration of the reactant. Whatever amount of reactant you take, it does not depend on that. That is the interest. Right. It is independent. Now, if you plot that okay, now here I am discussing another question that suppose if we plot reactant concentration at any time R versus time t, then it follows this curve, right? It would be exponential in nature. Now, if we ask you one fundamental question, that is the first order reaction will follow the zeroth order time at the very beginning of the reaction. Can we justify? The reaction in general follow the first order time, but under special condition, that is, what is the condition? The very beginning of the reaction. That is when just at the moment of start of the reaction, if you follow the kinetics, then if this first order reaction follows zeroth order kinetics, how will you explain that? That is the question. Not only first order, second order reaction will also follow the zeroth order kinetics at the very beginning of the reaction. Right. This is the fundamental question. So how you can explain that? Look, we start with the integrated rate equation. That is R equal to R0 in t to the power minus kt. And if we expand this exponential term in the power series, right, integral expansion, then we can write R0 into 1 minus kt plus k square t square by 2 factorial minus like that k3 t cube by 3 factorial and so on. So as we have considered the reaction at the very moment, at the very start of the reaction, very starting point, that is when t is very small, and in that time limit we can ignore the higher order terms in the series. That is t squared, t cube, t4. Ignoring all these higher order terms in t, what we write, the reactant concentration R at any time t can be approximated like this, R0 into 1 minus kt. And if we write it in the explicit form, that is R0 minus R0 into kt. Now R0 is constant because it is the amount of reactant concentration at the very beginning, that is at t equal to 0. At the start of the reaction, what is the reactant concentration? It is R0. K is the rate constant. If the reaction is carried out at a particular temperature, it is also a constant. So this product, that is K into R0, is equal to K prime here. Now this equation, R equal to, so first order reaction ultimately becomes equal to what? R equal to R0 minus K prime T, right? And if you plot that, that is R versus reactant concentration versus time, you see this exponential curve at the very beginning, that is within a very small time scale, you see we can trace a straight line at the very beginning, right? tangent is just like this. So what we conclude, this is nothing but this pattern, that is reactant versus T, if we plot the straight line. We already discussed here. So this pattern is similar to here. Or if you differentiate, you can write minus dr, right? Minus dr dt equal to k prime minus dr. If you just differentiate it, you will get it, the differential rate equation for zeroth order kind. So what we see that within a very small time limit, at the very beginning of the reaction, the first order, the reaction which follows eventually a first order kinetics can follow a zeroth order. Is it clear? Or if you have any questions, please clarify. Hello?
Yes, sir, we are there.
Are you getting me?
Yes, sir.
Yes, sir.
Yes, sir. So is it all right? That is how we can justify that a first order reaction will follow the zeroth order kinetics at the very beginning. Okay.
Okay, sir, I got it.
Okay. Now, this is the rate equation of zeroth order kinetics, the differential and integrated that I have shown. Yes, there is another similar question that you can do yourself. Following the same spirit, show that a second order reaction can follow a zeroth order kinetics at the very beginning. So you can do it yourself. Okay. So this is a home assignment, small home assignment, so that a second order reaction can follow a zeroth order kinetics at the very beginning.
Sir, I have a question.
Yes, yes.
Sir, any nth order reaction can follow a zeroth order reaction at the beginning?
No, not necessarily.
Only first and second order.
Not necessarily first or second order, because the question is, if you look at a typical second order reaction, there are two types. If it is a single reactant and second order, then it's okay. If it's two reactants, more than one reactant taking part in the chemical reaction, suppose A and B, right? Then that this kind of plot you cannot get, right? And in that case, it is not. So this is for simple first order, simple second order, right? For those reactions.
Okay, sir.
So here, second order reactions that proof you can do, that is like dr dt equal to minus dr dt equal to k concentration of reactant r square. So that you can use, right?
Yes,
For a
sir.
single reaction. Okay. Now for first order reaction, reactant to product, we generally find the integrated rate equation in the form that is in terms of reactant versus time. That is popular. Most of the textbook is written R equal to R0 in T to the power minus Pt. But can we write this equation in this form? That is product versus time. And what should be its form? Is it the expressions that I have written? That is concentration of product equal to reactant concentration into 1 minus e to the power minus Kt. Can we write in this form? That you have to verify. So from typical plot, as you have noted in the first order reaction, reactant versus time, reactant concentration decreases exponentially. So at time t equal to infinity, asymptotically, the reactant concentration tends to 0. Right. Limiting value of reactant would be tends to 0 when t is extremely large. So this is asymptotic behavior. Now product concentration. How we can write? We can write, if we write in the form that is this product concentration equal to R0 into 1 minus e to the minus kt. Now once again, at the limiting value, t tends to infinity, right? What happens? Product concentration will be equal to R0. Right. Limiting value. Yes, it is correct. No problem. There is no confusion. So in that way, that is, if we follow this limiting behavior of reactant concentration and then product concentration, then it's all right. But how we can derive it? For that, you see that we can write just in this form. Yes, that I'm discussing with you. That is reactant to product and product to reactant. Okay, that features I consider later on. Okay, but here to prove it, say R to P at T equal to 0. Let A is the number of moles, initial mole numbers of reactant AR, and V is the volume of the vessel where the reaction is carried out. So V is fixed. So we can write T at time T equal to 0, at the start of the reaction, product concentration is 0 and that of reactant is A by G. Now at time T, let X is the number of moles that is produced from A of the reactant. So the product concentration would be X by V. And R would be equal to A minus X by V. Now, what is R0? A by V. So from these two expressions, it is clear that we can write R0 minus R, that would be equal to what? R0 minus R, what is that quantity? Okay, you just write down what is R? R0 into e to the power minus kt. Can you write? In the right hand
Yes,
side?
sir.
You just subtract
Yes, sir.
from R0 both sides of the further integrated equation. And R0 minus R, if you follow these expressions, that is A by V minus A by V, X by V. It is nothing but product concentration P. Okay. Because we have considered R to P, the stoichiometric coefficient in the both sides is unity. So this is an ideal case. That is, one molecule of reactant after decomposition will produce one molecule of product. So from the conservation of mass, and if we ignore the reverse reaction, so naturally whatever amount of reactant that will be left, and what is the amount of product that is produced, the sum of these two at any time should be constant. That is what I say, that is R, concentration of R plus P equal to R0. Right. From that conservation, you can write directly, that is R0 minus R equal to P. Or just from this algebraic manipulation, you can also write it's P equal to R0 into 1 minus e to the power minus K by T, A minus KT. Right? So this is straightforward. Either you can guess that the reaction, first order reactions, it is considered as, that is, ignoring the backward reaction. Second thing is, it is in the constant vessel. The reaction is carried out in closed vessel. So there is no question of leaking out of any either the reactant or product. So whatever the reactant transforms to product, that we can strictly maintain that conservation of mass, that concept, and so we can, on the basis of that, we can write concentration of P at any time, that is concentration of product at any time during the progress of the reaction, and the corresponding reactant concentration. If we take these two at any time, that sum must be constant, that is R0. And from there we can see this difference in the left hand side is nothing but the product concentration. And we can write this. Or you simply manipulate like this, whatever algebra I have followed here. Anyway, it doesn't matter. Now at this stage, do you have any query? Please raise any question. If you have any doubt. I think it's all right.
Yeah, yes, sir.
Yes. Okay. Now, the thing is that if we allow the reverse reaction, the forward reaction is first order and say backward reaction is also first order, then we call this kind of reaction a reversible first order. That is R2P, that is reactant to product formation. This reaction follows first order kinetics, and the backward reactions, that is product to reactant, these also obey first order kinetics. And in that case, we say the reaction is we call reversible. This is a typical reaction. And in this reaction, you see, if you trace the reactant concentration versus time or product concentration versus time, it would appear like this. Just, you know, R equal to R0 into e to the power minus kt that we have plotted. And we also plotted the second equation, that is product equal to R0 into 1 minus e to the power minus. Right. That is product concentration increases. And it, look, the trend of the curve, as T increases, product concentration gradually rises to the limiting value of R0. And that of reactant concentration, it gradually falls up to what? Now, there is no question of zero. That I am addressing the point here. Because when T tends to infinity, the product concentration can never reach R0. If it reaches R0, then reactant concentration will fall up to 0. But it cannot take place. Ultimately, what happens? Product concentration quickly saturates, means it would be insensitive to the variation of time. Likewise, reactant concentration will no more change with time. That means at a larger time, or if we consider a long time, allow longer time, this reaction would attain equilibrium state. Right? That is, product concentration can never reach to the reactant concentration, or reactant concentration can never goes to 0.
Sir,
So this will be the fate of equilibrium, as you know. Yes, any question?
sir, the class is running.
Okay.
The class is exceeding its time limit.
Okay. Thank you for your information. So I think this is the end of my class. Okay, thank you.